Perceptron. This tool helps you understand the concept of perceptron in neural networks. A perceptron is a fundamental building block of artificial intelligence and machine learning. Think of it as a simplified model of a neuron in our brain. It takes inputs, multiplies them by their respective weights, adds them up, and applies a threshold, also known as the activation function, to determine its output. This output is then compared to the desired output, and the perceptron adjusts its weights using a process called gradient descent to minimize the difference between the actual and desired outputs. Essentially, the perceptron learns from data to make predictions or classify new examples, just like how we learn from examples to make decisions in our lives. This tool will help you understand the concept of perceptron. Let's explore it. To understand perceptrons, we have provided 4 examples here. The AND gate with step activation, OR gate with step activation function, AND gate with sigmoid activation function, and the OR gate with sigmoid activation function. Basically, these are combinations of AND or OR gate examples with step and sigmoid activation functions. These are probably the easiest examples to understand how a perceptron works. Let's select the first example, AND gate with step activation function. Here are the 2 inputs, x1 and x2, the weights w1 and w2. These weights are taken from a model already trained on the AND gate function. Here is the bias, which is another learning parameter, just like the weights w1 and w2. The bias allows the perceptron to make decisions even if all input values are 0. This is the weighted sum expression. As we can see, if we multiply this 0 with 0.6, it is 0. And if we multiply this 0 times 0.5, that is also 0. And finally, the only value that contributes to the sum sigma is this b, with a value of negative 0.8. And therefore, the sigma is equal to negative 0.8. Now we apply the step function, which uses this formula to calculate the output. If x is less than 0, the function returns 0. And if x is greater than or equal to 0, the output is 1. In other words, for any negative input value, the output of the step function is 0. And if the input is 0 or positive, the output of the step function is 1. Since in our case, the input to this step function is negative, the output is 0. Now let's change the input data by pressing this button, Next Data Input. The new input is x1, which is still 0, and x2 has now changed to 1. So in this sigma expression, the x1 w1 is 0, and the x2 w2 becomes 0.5. And when that is added to the b value, which is negative 0.8, the total sum becomes negative 0.3. Again, that's by adding 0.5 and negative 0.8. Because this sum is still less than 0, when it passes through the step function, the output is still 0. Let's select the next input data. By applying these weights to this data and adding the b value, the sigma is now negative 0.2, and the output is again 0. Finally, we can select the last input data. This time, the sigma value is positive and is greater than 0. So the step function gives a value of 1 as its output. Let's run the simulation again. With input 0, 0, we get the output 0. With 0, 1, we still get the output 0. With input 1, 0, the output is again 0. And finally, with the inputs 1, 1, the output is now 1. With this demo, we can say that this little perceptron has successfully demonstrated the functionality of an AND function. Similarly, we can explore the OR functionality by selecting the example OR gate with step activation function. Now let's try an example of a sigmoid function. Let's select the example AND gate with sigmoid activation. The main difference between this example and the previous AND example is that we are using the sigmoid as the activation function. The sigmoid activation function is a smooth, continuous function that maps any input value to a value between 0 and 1. This function is expressed using this formula. Unlike the step function used in a previous example, which outputs either 0 or 1 based on a threshold value, the sigmoid function provides a more gradual transition from low, which is 0, to high, which is 1. In this example, with the input as 0, 0, and these weight values, you can see that the sigma value is negative 8.307. As we pass this value through the sigmoid function, the output is 0. Let's move to the next input. The input to the sigmoid function produces a small output value. The next input produces the same output. Finally, for inputs 1 and 1, the sigmoid input is a positive number and falls in the linear exponent range, and therefore produces the output as 0.933. Using the same sigmoid as the activation function, you can explore the OR functionality by selecting this example, OR gate with sigmoid activation. This covers how this tool can be used to understand the concept of perceptron in neural networks. Please feel free to try this tool by using different examples provided and observing the perceptrons and its behavior.